Welcome to all. In this class, we are going to see the performance characteristics of the instruments. Generally, the characteristics of the instruments is classified into two types, static characteristics and dynamic characteristics. In this class, we are going to see what are all the static characteristics and dynamic characteristics of the measuring instrument. First, let us see what is the static characteristics of the instrument. The performance characteristics of the instrument is classified into two types. One is static characteristics and second one is dynamic characteristics. First, let us see what is static characteristics. The characteristics of the instrument which is used to measure the quantities which are slowly varying or almost constant. So, static characteristics, the characteristics of the instrument which is used to measure the quantities which are slowly varying or almost constant. Almost constant is in the sense it does not varies with time. So, there are many static characteristics of the instrument. We will see one by one. The first static characteristics is accuracy. So, here the accuracy is defined as it is the degree of closeness with which the instrument reading approaches the true value of the quantity to be measured. The first static characteristics is accuracy, which is the degree of closeness with which the instrument reading approaches the true value of the quantity to be measured. In short, we can say that it denotes, that is, the accuracy denotes the extent to which we approach the actual value of the quantity to be measured. It also indicates the ability of the instrument to indicate the true value of the quantity. Let us see the example for accuracy. Example, we are taking a readings taken by a person called John. He measures the amount of juice in his mug. He measures the amount of juice in his mug 3 times. He measures 3 times the amount of juice in his mug. So, he obtains the following result. One is 119 ml, 118 ml and 120 ml. He obtains the 3 readings. The first reading is 119 ml, second one is 118 ml, third one is 120 ml. But the actual value of liquid or juice in the mug is 120 ml. But while measuring, he measures 119 ml, 180 ml, 120 ml. 190 ml is 1 ml away from this actual value, and 180 ml is 2 ml away from this actual value, and 120 ml is equal to the actual value. So, the closeness with which the instrument reading approaches the true value of the quantity to be measured is called as accuracy. So, we can say that 120 ml is most accurate reading, that is most accurate value of the amount of juice in the mug, and 119 ml and 118 ml or 1 ml and 2 ml away. So, from this we can say that 118 ml is the least accurate value which is measured. This is the example for accuracy. Now, let us see the second static characteristics, which is precision. It can be defined as the measure of consistency or repeatability of measurement. Measure of consistency or repeatability of measurement is called as precision, or else we can say that it is the degree of exactness which an instrument is designed to perform. So, the measure of the consistency or the repeatability of measurement is called as precision. Otherwise, we can define precision as the degree of exactness with which an instrument is intended to perform. Let us see the example for precision. A person called John measures the amount of juice in his mug. He obtained 4 readings. The first reading is 100 ml, second reading is 101 ml, third reading is 102 ml, and the fourth reading is 101 ml. But the actual value of the actual amount of juice in his mug is equal to 120 ml. So, by seeing this readings, we can say that from the definition of accuracy, none of these values obtained or measured is nearer to the actual value, that is 120 ml. So, we can say that these readings or the instrument which is used to measure these readings is not accurate, which is the first static characteristics. Now, let us see what is precision. But while observing these readings, we can see that the difference between these 4 readings is very closer to each other. So, the readings are closer to each other. So, we can say that the difference between 100 and 101 is 1, 101 and 2 is 1, and 102 and 101 is 1. So, we can say that the readings are very nearer or closer to each other. So, we can say that the precision is high, but none of the values is nearer to the actual value. So, we can say that these readings are not accurate, but the readings are very near to each other. So, we can say that the precision is high and the accuracy is poor. Now, let us see the difference between accuracy and precision. So, we have seen 2 examples for accuracy and precision. Now, let us take a person measures the volume of juice in his cup. The actual value of or the volume of liquid in his cup is actual values 20 ml. The actual value of the liquid in a cup is 20 ml. A girl measures the amount of liquid in a cup, which is 20 ml. But while measuring, she obtains the following readings. The first reading is 20 ml, 19.3 ml, 18.8 ml and 18.7 6 ml. So now let us find the accuracy and precision of this readings, that is first readings. We know that the actual value is 20 ml. She obtains the following readings. What about the accuracy of this readings? We know that the actual value is 20 ml. If you see the 4 readings, we can say that the first reading is equal to the actual value 20 ml. So we can say that the accuracy of the readings and the instrument is good. What about precision? We know that precision is the closeness with the measured readings. So we can say that the difference between the readings is high, that is 20 ml, 19.3, 18.8 and 18.6 ml. So we can say that the precision is poor in case of this readings. Now let us take another example, that is 18.6 ml, 17 ml, 15.6 ml and 16.2 ml. The same case, the actual value for this readings is 20 ml. None of the readings is equal to or nearer to the actual value, that is 20 ml. So we can say that the accuracy is poor for this following readings. What about the precision? The difference between the values is also not closer to each other. So we can say that the precision is also poor in this case. Now let us take another example, that is 20.1 ml, 20 ml, 20.2 ml and 20.1 ml. The actual value is 20 ml. What is the accuracy? The accuracy is high because 20 ml is the actual value and the other readings are very nearer to the actual value. What about the precision? So the difference between these readings is also very nearer to each other. We can also say that the precision is high or good. Can say that high or good. Accuracy is high or good. Now let us take an bird's eye target as an example for accuracy and precision. In this, I am going to represent the inner circle, which is the actual value, and it is the outer boundary. Okay, this one is the actual value, this one is the outer boundary. I am going to represent the reading which is measured readings with the help of a dot. So this is the actual value, right? So I am going to mark the readings with a dot here. I have taken 5 readings, that is 1, 2, 3, 4 and 5. If you see that this is the actual value of the quantity to be measured, one of my reading falls inside this actual value and other readings are scattered outside the actual value. Now we will see what about the accuracy and precision in this case. So if any of the measured reading which is represented by dots is within this actual value, we can say that the accuracy is high or good. What about the precision? The readings has a greater difference, so that it is scattered inside this outside boundary. So we can say that the precision is low or poor in this case. Now let us take another example. I am drawing the outer boundary. This is the actual value. I am marking this 5 readings here. 5 readings falls here. What about the accuracy and precision? So the measured readings represented by the dots. So none of the readings fall inside this actual value. This one is the actual value boundary. So we can say that accuracy is low or poor in this case. What about precision? Precision is nothing but the closeness of the reading. The difference between the reading is very close, so that the readings are very nearer to each other. So we can say that the precision is high. Let us see another example. Drawing the outer boundary and the inner boundary actual value. I am marking the readings. What about the accuracy of this system? We know that accuracy is, this is the actual value boundary. Here we can see that the 5 readings falls inside this actual value. We can say that accuracy is very high in this case. What about precision? Precision is also very high because all the readings are very closer to each other. So let us take another example. I am marking the 5 readings like this. What about the accuracy in this case? Accuracy is very low because none of the readings falls inside this actual value. And what about precision? The difference between these readings is very high, so that all the readings are scattered out around the outer boundary. So we can say that precision is also very low. Now I think that we have got an idea about what is accuracy and precision and what is the difference between accuracy and precision. Next we will see the 2 components in precision. So precision has 2 components. One is the number of significant figures . Second one is conformity. First let us see what is number of significant figures. So it is defined as the meaningful digits used to express a numerical value, that is measured value of the quantity. It is known as the number of significant figures, right? So it is the number of meaningful digits used to express the numerical value, that is the measured value of the quantity, or the quantity which is to be measured is expressed in number of meaningful digits. So it points out the preciseness of the measurement and the measured value. Let us see the example for significant figures. Example, if a person measures the voltage across capacitor as 50 volt. If he measures the voltage across the capacitor as 15 volt, it means the value nearer to this 50 volt may be 49 volt or 51 volt. Indicates measured value may be between 49 to 51 volt. So in this case we can say that the measured value 50 volt has 2 significant figures. I am representing significant figure as SF. The same case, if he indicates this measured value 50 volt as 50.0 volt. Now in this case we can say that this 50.0 volt is between 49.9 volt and 50.1 volt. So in this case we can say that the number of significant figure is 3, which has 3 significant figures. Also we can say that the preciseness is high because the difference between the reading is high if you represent the measured value as 50.0 volt. There are certain rules which is to be followed while finding the number of significant figures. We will see the rules for finding the number of significant figures. First rule is non-zero digits are significant figures. Non-zero digits are significant figures. Example 4362. So it has 4 significant figures. It is a non-zero digits. So we has 4 digits in this. 4362, 4362 has 4 significant digits. So we have to consider the non-zero digits. The second one is all zeros occurring between two non-zero digits are significant figures. Example 1005. So we have to consider all the zeros which is between the two non-zero digits, that is this case 1 and 5 are the non-zero digits. The zeros which is in between this two non-zero digits is to be considered for calculating the number of significant figures. So in this case we have 4 significant figures. And third one is all zeros to the right of the last non-zero digit are not significant. Example, you are having a number like 6250. So all the zeros to right of the non-zero digits, that is the zero at the end of the non-zero digits, are non-significant. So there is no need to consider this zero. So while calculating the number of significant figures, here we have only 3 significant figures. And the fourth point is all zeros to the right of the a non-zero digit in the decimal part are significant. Example 1.4750. So you have to consider all the zeros to the right of the non-zero digit in the decimal part, which is to be considered for calculating the number of significant figures. So in this case we have 5 significant figures. And fifth rule is in digits like less than 1, all zeros to the right of decimal point and to the left of non-zero digit are not significant. Example, you are having a digit which is less than 1, that is 0.00325. So there is no need to consider the zeros which is to the left of the non-zero digits and to the right of the decimal part. So here the number of significant figure is 3. Have to consider only the non-zero digits, and we have to omit the zeros which is to the left of the non-zero digit and to the right of the decimal part. Now let us see what is conformity. Example for conformity is we are going to measure the value of a resistor. So its value is measured as 2385692 ohm, which is measured using a multimeter. By using a multimeter, we have measured a resistor whose value is 2385692 ohm. Okay. So if you see that while measuring this value of resistor, the multimeter will consistently measure the actual value of the resistor, which is 2385692. But while taking the readings, the reading will the meter will consistently show the value as 2.4 mega ohm. Due to non-availability of the proper scale, the resistor value is shown as 2.4 mega ohm by the multimeter. But the actual value of the resistor to be measured is 2385692 ohm. But due to non-availability of proper scale, the meter measures the value as 2.4 megaohm. Although there is no deviation from the actual value, due to the limitation of the scale, the precision error occurs while taking the or while measuring this resistor value, which is 2385692 as 2.4 megaohm. So this is the example for conformity. So from this we can say that conformity is necessary condition but not sufficient condition for the measurement to be precise. So for the measurement to be precise, conformity is a necessary condition but not the sufficient condition. Similarly, we can say that precision is necessary but not sufficient condition for accuracy. It is necessary but not a sufficient condition for accuracy. So we can say that accurate system should be precise but a precise system should not be accurate. This is third static characteristics, which is error. So generally accuracy is expressed in terms of error. So we can calculate error, can say that absolute error or error can be calculated from the true value and the measured value. That is, absolute error, which is represented as E, is equal to the difference between the true value, which is represented as AT, and the measured value, which is represented as AM. So the difference between the true value and the measured value is called as absolute error or error. So while measuring the error, if you want to measure a voltage in the range of 5000 volt, the absolute error of plus or 1% is not significant, so we can neglect this value. So we can neglect while measuring 5000 volt, the absolute error of plus or minus 1% can be neglected. But if you want to measure 5 volt, in this case absolute error of plus or minus 1% is significant. It creates more error. So instead of mentioning this absolute error, the error is expressed in terms of relative error or percentage error. So the relative error can be calculated as, it is represented as ER, which is equal to absolute error divided by true value. You know that absolute error is equal to true value minus measured value divided by true value. So we can represent relative error ER as AT minus AM divided by AT. This absolute error divided by the true value. So for relative error, the accuracy can be expressed as accuracy A is equal to 1 minus ER, which is 1 minus AT minus AM divided by AT. The percentage accuracy can be written as A into 100. Next we will see the next static characteristics, fourth static characteristics, which is sensitivity. It denotes the smallest change in the measured value to which instrument responds, or you can define sensitivity as, it is defined as the ratio of change in output of the instrument to change in value of input. Input is nothing but the quantity to be measured. So, we can write sensitivity or define sensitivity as sensitivity is infinitesimal change in output divided by infinitesimal change in input. That is small change in output corresponding for the corresponding change in input. If you draw the calibration curve, which is the curve between the input and output characteristics, so which is represented as Qi and Q0. If the calibration curve is linear, if you draw the calibration curve, if it is linear, the sensitivity of the instrument will be equal to the slope of this calibration curve. If you calculate the slope of this linear curve, that is small change in input to the small change in output, the slope value gives the slope of the instrument is equal to sensitivity. This is the case when the characteristics is linear. If the characteristics is non-linear, the calibration curve drawn between the input and output is non-linear, that is, if it is like this means, so the sensitivity varies with the output and it is not equal to the slope of the instrument, because if we here find the slope here means you will get the slope value as del Qi del Q0. So, here the slope will be like this, that is del Qi and del Q0. So, here the sensitivity varies with output. The sensitivity varies with output. So, here the calibration curve is linear and here the calibration curve is non-linear. So, sensitivity is the ratio of infinitesimal change in output to the infinitesimal change in input. Now, let us define what is deflection factor. So, deflection factor is nothing but the inverse of sensitivity, which is del Qi divided by del Q0. That is infinitesimal change in input to infinitesimal change in output is called as deflection factor or inverse sensitivity. See the next static characteristics, which is resolution. The smallest measurable input change, the smallest measurable input change is called as resolution. So, if a non-zero quantity is slowly varying with time, for the small change in input there will be a small change in output. So, that is called as resolution. We can say that the smallest measurable input change is called as resolution. The sixth static characteristics is threshold. So, threshold is nothing but the minimum change in input for output to change is called as threshold. So, we have seen that resolution is the smallest measurable input change. So, threshold is nothing but the smallest measurable input. So, resolution is the smallest measurable input change and threshold is the smallest measurable input. So, there must be a minimum change in input so that the output starts varying. Until that minimum value of input is reached, the output will not change. So, that value where the output starts to change or vary is called as threshold value. The next static characteristics is linearity. So, it is nothing but the ability to reproduce the input characteristics symmetrically and linearly is called as linearity. That is, output varies linearly with input. If example, output of any instrument varies linearly with input, we can say that system is linear. That property is called as the linearity. The next static characteristics is drift. It is the gradual shift in instrument indication over an extended period during which the value of input variable does not change. So, it is a gradual shift in the instrument indication or reading over a extended period during which the value of the input variable does not change. So, if you see the characteristics like this, say input versus output characteristics, initially the characteristics is like this and there is a gradual shift in this instrument reading, so that the reading is moved to a, there is a difference between these instrument reading and there is a shift between this indicated readings. So, it is called as zero drift, but the value of input variable does not change. The ninth characteristics is range or span. It is the minimum and maximum value of a quantity for which an instrument is designed to measure is called range or span. For example, if you take a thermometer reading, the thermometer is calibrated between 200 degrees Celsius to 500 degree Celsius. So, the range of the thermometer will be the maximum value, which is the 500 degree Celsius. What about the span of the thermometer, which is the difference between the minimum and the maximum value? That is, minimum value is 200 degrees Celsius and the maximum value is 500 degrees Celsius. So, difference between these two minimum and maximum value of the thermometer gives the span of the thermometer, which is 300 degrees Celsius. So, the difference between the minimum and maximum value gives the span and the maximum value gives the range of the instrument. Next, we will see the dynamic characteristics of the instrument. We have seen the 9 static characteristics. Now, we will see what is dynamic characteristics and what are the dynamic characteristics of the instrument. The characteristics of the instrument which are used to measure the quantities which vary with time is called dynamic characteristics or the dynamic response of the system. So, the characteristics which are used to measure the quantities which vary with time is called as dynamic characteristics or the dynamic response. Let's see what are the dynamic characteristics of the instrument. The first dynamic characteristics is speed of response. So, the speed of response indicates the activeness of the system. So, it is defined as the rapidity with which the system responds to the changes in the quantity to be measured. It is the rapidity with which the system responds to the change in the quantity to be measured. How rapidly or how quickly the system responds to the change in the quantity to be measured is called as the speed of response. So, it gives the information about how the system reacts to the change in the input. The second is fidelity. So, it indicates how faithfully the system reproduces the changes in input. How faithfully the system reproduces the changes in the input is called as fidelity. So, we can also say that it is the ability of the instrument to produce a wave shape identical to wave shape of input with respect to time. So, the ability of the instrument to produce a wave shape identical to the wave shape of the input with respect to time is called as the fidelity of the instrument. Third dynamic characteristics is lag. So, it is the retardation or delay in the response of the system is called as lag. So, lag is nothing but the delay or the retardation in the response of the system to the change in input is called as lag or measuring lag. So, generally every system takes some time, whatever small it may be, to respond to the changes in the measured variable. So, there are two types of lag. So, lag is given to two types. One is retardation lag and another one is time delay. The fourth dynamic characteristics is called dynamic error. It is the difference between the true value of the variable to be measured changing with time and value indicated by the measuring system assuming zero static error is called as dynamic error. Let us see the characteristics. If you draw the characteristics of the instrument, it is the input and output characteristics with respect to time. We are getting a characteristics like this. So, this characteristics represents the true value or quantity to be measured but if you draw the characteristics for the instrument reading, we are getting a characteristics like this. So, there is a difference between the true value or the quantity to be measured and the instrument readings. So, if you draw the characteristics for the quantity to be measured, that is the true value of the quantity to be measured, and the characteristics for the instrument reading, we are getting two different characteristics, that is there is a dead time between these two characteristics, and if you see this, there is a difference in two readings. So this difference is called as dynamic error. So the difference between the two value of the variable to be measured changing with time and the value indicated by the instrument reading assuming the zero static error is called as the dynamic error. Thank you.